The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, the group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everyone, I am geologist Philip Ong, here with Mr. Dane DuPont, HawaiiTracker.com, bringing you guys another volcano update. Today we're going to cover both Kilauea and Maunaloa as we switch to a weekly schedule here for the foreseeable future until. So Kilauea has stopped erupting officially according to the USGS. We will cover that and cover details of that. You guys are looking at the F1 thermal camera here live. Last 24 hours showing not much activity, just some remnant heat on the surface, still hot underneath there. And we will start with Maunaloa, looking at some of the signals there before we cover Kilauea signals and talk about what might happen next. We'll collect questions, then we'll collect questions, man our chats, check our streams. If anything's wrong, let them know. Otherwise, we'll collect questions and we'll take a question intermission partway through and then once again at the end there. And if you guys have any Maunaloa questions, you can get them in early. We'll try to answer those first, as we will focus to what everyone is talking about this week, which is that Kilauea is officially downgraded. See the main USGS page right here is now switched over and now says recent Kilauea volcano eruption. The Kilauea volcano is erupting like earlier in the week. And all the same kind of links, but if we scroll down, we can also see that Kilauea is now at yellow advisory. Kilauea is now at yellow advisory over there. So Text. Same as Maunaloa now, so both volcanoes have the same status of elevated activity, but not actually at this point. Besides erupting, if it's a threat to people, then you might go into the red as well. So we weren't even at that on Kilauea. We were on yellow here. Right, so but we'll start with Maunaloa. There's a view of Maunaloa as seen from that south side of Kilauea, that collapse. Greater Rim Drive right around here, bottom left. And there's not a lot to talk about Maunaloa, but we will go through it. Maunaloa, the earthquakes here over the last month. Not a whole lot in that summit region. We'll turn to the iris animation here. One here. So this is the last month. Guys, here the last month of earthquakes, and there are a few earthquakes happening still in the northwest area early on. We're getting more in this Kauiki area. That's the interface between Maunaloa and Kilauea. Maunaloa's south flank that tries to move off in this direction, and Kilauea, of course, in the way, and having to alter those plans, of course. So still some adjustment on the south flank here, but nothing major, nothing as quick or as active as we've had previously. About a month and a half of quiet now in Maunaloa. You can see that on the earthquake rates here for the past year. Really, the beginning of April was the last peak and really ramped down substantially since then. On from there, the activity update from Maunaloa this week. Business as usual. The number of earthquakes reported is only 39 this week, so that really is a good indicator of how few earthquakes are occurring. Similarly, all less than 3, all depths with about 5 miles within. Otherwise, not a whole lot of change in the update because there's really not a whole lot of change in the signals. Here's our tilt and GPS signals. Here's tilt in the last month. Some little bit of wiggle coming up here, but still, it's hard to link that to any convincing volcanic pattern underground with that small magnitude there. And looking at the GPS caldera distance change, that has also stayed at that slow, maybe a slight expansion here, slightly going upwards, but still quite a bit slower than I was doing beforehand. It seems to be in neutral almost. Their analogy we've got to use. Waiting something else to change there. So not a whole lot on Maunaloa. That's it. We've touched all the bases of Maunaloa, so we will move on unless anyone has any particular Maunaloa question. And if anything urgent does break, remind you guys that is going to be put up on Hawaii Tracker.
We do have one question from Earl on Facebook who asks, as far as the eruption possibility, what side of the mountain is more likely for a flow? Is there any way to know?
Not really. It's all about where it comes out. First of all, which area of the volcano, and we expect it to be the summit first, which is far away from people, and then the upper rift zone areas, which are also far away from people. And then if it migrates down one of the rift zones, then you know more or less which quadrant it's going to be in. But then since the rift zones are ridges, they're the high points, it matters whether it flows down to the west or to the east. And only when it leaves that rift zone area, it starts going one of those directions, or possibly both at the same time, can you really say, okay, now it's going somewhere we can tell. At that point, you really can't tell. It can meander within the rift zone. It could actually, if it splits both ways, it's good because lava doesn't all go to one place. It kind of spreads itself out, and half not as powerful, put it that way, right? So, yeah, very very specific when it comes down to it.
All right, well, that will do it for the Maunaloa questions. I'm sure we'll have more as we progress. And if you have any more questions, drop them in the chat and we'll get them in the next segment.
Mahalo Dan, mahalo for the Maunaloa question there. So we're turning to Kilauea, and the big news this week is first an update on Wednesday, followed by Wednesday night issuing of a new VAN, volcanic activity notice. These don't come out very often, only with a major status change. So this is something above and beyond, right? And Kilauea volcano is no longer erupting. They finally made a determination that lava was last visible to surface on May 23rd. That was actually a couple days before our last update, but it took to the day afterwards for them to actually make the downgrade. A lot faster than previous eruptions, as we talked about the end of last update. So that's great to see. And in the notice, which came in essentially 3 parts, right? We have the DAN here, which has a lot of details as far as the observations and remarks. There's also an aviation notice that was put out. And finally, to add on to it, there was also published yesterday was a Volcano Watch article, which goes into even more detail. So we have a lot of information on Kilauea here at the end of the week, all of a sudden relating to the end of the eruption, as is necessary to validate the downgrading of the volcano status here. So that's why we were going to spend more time focusing on information we actually do have here. So I'll kind of go through a little bit of the highlights first, and then we'll go through and show you guys on data. I try not to spend too long on this text part here. But you can see that there's still fume coming out. They essentially are still seeing signs of magma coming into the volcano. It is pushing the tilt meter to slow inflation. It is causing seismicity under the summit and in the upper rift zone. Otherwise, apparently the lava level has stopped coming up. The gas is still not coming out. Any elevated levels, that would indicate that the lava is coming out as well. So the gas has gone down enough that we believe the lava is not coming out anymore. Not even beneath that crust. That crust is no longer rising upwards. And they do detail in here. Supply to the lava lake appears to have ceased between May 11th and 13th. Those are 2 dates we've discussed before when looking at the lava level graph. Look at that again. They do say completely crusted over by the 20th, with a couple last surface activity events last observed on the 23rd there. So if we're using last lava on the surface as the end of the eruption, that's the date, May 23rd. That makes it 153 days, I believe, of total eruption. We'll wait to see what the official number is, but that's my tentative educated guess there. Since May 11th, weak inflation, increase in shallow volcanic earthquake at the summit, suggesting magma entering the system is being stored at depth. So they do say it's paused. It's possible it could resume or entering quiescence prior to the next eruption. So let me see if there's anything else that's really necessary to pull out from this one. I'll move on from that one. The aviation notice, not a whole lot that I'll pull out for you guys from there, but it's a lot of that same kind of activity, and showing that there's no aerial hazard there, since there's nothing really coming out of the ground. And the volcano watch really was what gave us the final pieces of information we needed to tell a story of what might have happened as far as why the eruption might have stopped here. And this is essentially focusing on the elevations. So along with a move here to this image released with the Volcano Watch yesterday, is showing all these different profiles of the crust elevation with the islands and the levees and everything at different points, different dates during the eruption here. So pre-eruption is the black, and then you can see yellow is December 20th to 30th is that first whole bunch of it, then January a little bit, and February through May the rest of it there. And essentially, the west vent is over here to the left, and that original elevation of it is where the lava level is now. So that's the reasoning that's been put out, and turn back to the Volcano Watch here, and I'll actually highlight it for you guys. And of course, there's a lot of process, and they're trying to make everything understandable. So mahalo USGS for that. For giving us some stats in here early on. I'll come back to those in a second here, but so when they're talking about the SO2 decreasing, they do say eruption rates and SO2 gas emissions declined precipitously after April 16th, coincident with the level of lava in the lake reaching the level of the vent. This relationship suggests that the colder degassed lava within the lake essentially drowned the vent. So there's our first real statement from the USGS and what might have actually caused this to happen. And interesting that the pressure of the eruption was so passive per se that just that seems to be enough. And so far, it's been enough to keep it corked, right? Of course, and that's why the potential still exists for it to reactivate. It's not something that changed within a source. It was more in a nozzle. And if it's in equilibrium, then it's all good. It may be done for a long time. But it could also build back up and pop back out somewhere if it can build pressure underground. And that's wait and see over the next few weeks and months here. So they do mention lots of pauses. We'll come back to this as well. We mentioned 2018 before. They do mention Pu'u, of course, lots there. Maunaloa, Kilauea, 55 lower east rift zone. They do note that most eruptions, if they are paused and it will resume, do so within 3 months after pausing. So that right there is our window. It's 3 months. That's what we'll be on elevated alert, even though not actually. Okay. So this is a view from the side of the profile. This is all taken from these elevation models that are put together from that photo from motion, or motion structure from motion photography. And viewed from above, here are those lake elevation contours through mid-April, which is good enough essentially there. And you really can see how early on both the north vent and the west vent were elevated above that inner pool of lava. But as the lava level rises, first the north vent gets drowned and it shuts off. And then just recently, the west vent gets drowned and it also shuts off. You can see here this uppermost contour right in there. These upper contours essentially are at that above that initial shape of the vent there early on. So we did have that cinder and spatter cone that built up higher above here. Not that big, but like that. And even though that is a mass that was raising the whole structure, apparently there's some connection deeper down at the elevation of the crust right now. It's really the key component there. Okay, so SO2 emissions have gone down. Here's the last month. I don't know if it's worth reloading it here, but we're actually under 100. Back up above and from below, right around 100 tons per day still. So that's our essentially background level there. We'll have to set a new background essentially now with the lava not coming out and no water buffering the emissions of gas. So we'll see what the new background is, but it looks like it's right around that 100 level right there so far. And put it in perspective, here it is over the whole last year. So it's hard to see a little bit, but here's a measurement from before the eruption, centered right around 0. And we spike up to that 60, 50,000, go back down, and then finally tailing off back to that 0 point way over here again. Big picture of it there. Here is the lava level. So somewhere between May 11th and May 13th, 2 little injections there, right? That seemed to indicate lava was coming in below the crust and still pushing things upwards. So from this point onwards, there is no obvious supply coming in from below. And you could argue that this possibly is supply. It's not 100%, but it could be. And this one seems likely given the size of it. And so somewhere in there is when lava stopped coming in. So that might be one way to characterize the end of the eruption, May 11th to 13th. We've in the past discussed how Kilauea was reported to have had crust overturning for 10 days after the eruption was over. And this is back in 1959. And so if our lava stops coming in really on the 13th, and it takes 10 days for it to stop overturning, that's the 23rd, last lava on the surface 23rd, that's consistent. Perhaps by coincidence, but that does happen to be exactly the same. 10 days of crust overturning since the lava last injected crust there. And the whole lava lake crusting over around the 20th, that's the date right around here. And this particular spot, this laser rangefinder is pointing to a particular spot, it's fixed on the ground and it's pointing to a fixed spot on that surface. And they don't want to move it around all the time so it can be consistent, right? So that fixed spot, crusted over, it's probably right in here on the 5th or the 6th. You can really see how that pattern changes from this more wiggly oscillation here on the left to this stepwise pattern here on the right. Have this kind of crust, and then like it gets synced in and overturned and replaced and forms a crust. And here's our level of equilibrium for the crust, and then it gets lifted upwards, and that pattern continues. And that's what we're still seeing here today. Right? With this little still this little smaller oscillation still visible within that, and that's something that's interesting to look at, which we will do here next. But first, let's zoom out, show you guys the whole perspective of the whole 5-month eruption. And so that showing those contour lines in December, those first 10 days were when we gained most of the depth. And really since then, it was a slow climb, that next middle phase, and much slower increase here over the last couple months. If you look real close, zoom into it, you really can see these oscillations. Here they are, right? Note our scale in meters here on the left. 229.22.2, so we're going down 2 centimeters every one of these little hash marks. So this is a measurable change. It's not exactly clear just looking at it what exactly it is, right? You might notice it happens to be happening close to every 24 hours or so, right? It seems like the trough here is right at noon and every day just about that lowest spot in time. Interesting. And so looking into it a little more, I pulled up the seismometer. So the seismometer on the rim here is just kind of on the south side of the caldera. And the last 24 hours here, so you can see you can see a little bit of a pattern. There's bands where you have more of this longer drawn out ink. This is more of that harmonic tremor. And then times where you have less of that, and during those times of less, you have more of these discrete little pops, as little small discrete earthquakes, little earthquake. So smaller earthquakes instead of long drawn out vibration of some area there. So remember, we just pointed out that the troughs are happening at noon every day, and if you look, this is at first a little suspicious because you might think, well, it looks like it's 8 a.m. to 5 p.m. That's a working day for a human. So maybe there's someone driving a bulldozer around and there's construction in a park, but not next to the station, there isn't. So this is actually just happens to be a coincident signal. This is possibly something like gas or magma movement through some shallow conduits there, and possibly it is even venting of gas from that surface of that lake. If we turn back to the elevation plot, we can see that the level is actually dropping, like it's losing volume before it seems to lift again, and then it loses volume. And it's during this in-between time when it's dropping down in this lowest part is when you're seeing this darker ink. It's the in-between parts when you see it doing this popping back up. That's what it looks like. I'll show you guys where the station actually is here. It's that one right there, the rim on the south side of the caldera.
We have 2 super chats. First one is from 2 Pineapples. It says, appreciate the stream, Mahalo for all your updates. Aloha. Thank you to 2 Pineapples. And $9.99 super chat from Sunflower just has a emote thank you. So that's all it says. But we appreciate all the support on that.
Yeah, so just to show you guys, here's some other instruments, and you see this similar kind of pattern on all the seismographs here. Bit of alternating pattern there, and of course, the closer you go to this side of the park over here, that's where the cars drive. No vehicles can get past this intersection right over here, which is why I like to look at stations more over here or over here. So they're not always all linked. See, here's the Sand Hill station. So magma still moving down there. This down here might be more of a magma signal, perhaps, more so than these smaller. This might be more of that gas venting signal right in there. So I think there's probably a little bit of both going on, and of course all these other earthquakes adjusting in between. So still plenty happening. Dane is ready to start a pool on when the lava is going to come back. Because
I bet 6 months.
6 months, because there's some
That's what I was
signals
putting
there.
the money on.
Yeah, 6 months.
I just like that. I like that 1840 model. I mean, we were using that immediately after the 2018 eruption, saying, "Oh yeah, in 1840 there was an eruption within the summit within 3 years," and that seemed to work pretty well. So what happened after that 1843 eruption, or that I think there was one in 1841 even, right? We kept having more at the summit, very similar ones, until it had filled in the collapse pit. So I'm like, that seems like the story we're in, but that's just me.
Could be, yeah. There are also, just to, throw a wrench in there, there was another collapse in 1843 and another collapse in 1868. So hopefully we don't have that coming, but that is possible.
Right.
That there's more collapses. That the adjustment isn't quite over yet. It's a long, drawn out geologic process, and we see the whole thing in months as a human, and we think that must be it. There can't be possibly anything else. It really is. It could be a long, drawn out process over geologic time. Really. Yeah, fascinating that. So this is all on the USGS page. If you go to the monitoring map, you can find these stations and click around and look for some of those signals there. That is mentioned, right? It's mentioned by both in the Volcano Watch and an interview by scientist in charge Ken Han today, saying that there certainly is tremor there. That's noticeable. It's definitely gone down, but there's still signs of magma moving and collecting at depth instead of coming out of the volcano now. So let's look at that a little bit here. Information data. We are still going through deflation and inflation cycles. We're on our third back-to-back here. We have two big ones here this week. And overall, the pattern that began in mid-May of rising, not really clear what's happening here. There's too much deflation and inflation going on to tell where that's actually going. So it could have changed. It could, well, just go back up to like this, the next one, and then that'll keep our pattern going. So we're just still waiting for it to complete. Not enough information to see there. And looking at the GPS, same pattern as before. You really see that inflation of the volcano, magma still coming in, collecting at depth as it has been that entire time, apparently. Okay, so earthquakes over the past week increased under the summit. That's this region right in here. That's that summit. Increased activity right through there. You can see there's a little bit in the lower east, in the upper east rift connector right in here. Connector. Maybe a little bit coming into the range of this upper east rift zone to Pu'u. Pu'u is right here. But more so you see to the south of that rift zone, the south flank area that is moving. We actually had earlier in the month a bigger earthquake over in this area, and then just last week that 4.2 over here. Notice that's directly seaward from the summit. So you imagine if there's magma coming in, building in the summit right in here, it could easily cause earthquakes in this area and push this wall the only way it can go towards the summit and towards the ocean, and that would put pressure on this zone that was released through the earthquake. That's all interesting how that fits together. Still seems very much to be all in this national park region, kind of this triangle zone right in here, right, is where all the action is, which is fortunately in a national park. That means minimal human impact. The management of the park is such to protect people. So that, and no neighborhoods in the middle of there as well. So that's all good. This is all academic at this point. We do this, of course, to practice talking about this and learn process so that when lava comes into somewhere that's more populated, we are not all in shock and we focus our efforts intelligently.
We have a 1999 super chat from Dorothy on YouTube. Says, for the pool, love catching your information videos. Appreciate it. Appreciate all the support.
Hello, Dorothy. All right, so let's see. Might need to. Oh, nope, there the next responded. Having a little bit of a response issue. But here is a past month on Kilauea. And you see a very similar pattern. A lot around a summit, and the East Rift is a little bit more visible here. And maybe easier to see this pattern of south flank earthquakes down around in here. It's really worth. Let me interface here. But this upper East Rift connector area is easier to see in this whole month picture. Right? It also goes to show if the past week is dominating the last month's plot, that most activity, there's been more activity in it recently than farther ago in time. So let's see if I can recapture some response here from browser. All right. So this is a model we showed last week, this cross-section from Brown et al., 2010. And there is our summit caldera that's filling. And you can see that as it puts pressure to the south, it can all the way over here push this décollement slip and this whole south flank and move towards the ocean that way. And we're also seeing magma come in this upper east rift connector in here. That's also generating earthquakes above it, and that could be a response to magma filling these void areas that, you know, if they're not open and it's enough pressure, you can inject dikes like these ones shown on this diagram here. But even with lower pressure, if you don't have a full system, you can come and fill that space, and magma come in and go in and fill that honeycomb area that's available for the magma to occupy. That is the model there. On Kilauea, let's look here at the earthquakes animated over the past month. And a little more here. There's that 4.2 that just happened, so I think loop starts over here. You can see a little bit quiet to start, and then the flurry or the summit begins somewhere in the middle of May there. Right in there. You start seeing more activity on the south flank as well, coming in here. Not a whole lot of events. It's not the most dynamic animation there, but I just wanted to show you guys that for sure. Oh, Iris Earthquake Browser, Mahalo Iris. It may be easier to tell here. This is the earthquake rates for the past year. So clearly elevated before the eruption, and then peaking a couple times leading up to the eruption, which happens right around in here. Levels were decreased for a long time, and then maybe right around in here in mid-April might be when we actually see this slight increase, right? So it might be increasing or it's picking back up. We're still nowhere near the level of it looking like it might happen again immediately, right? It has to get back up to this kind of level for us to be talking about that. So we still have to ramp this up for however long it takes over time to get up to this elevated level to have some indication that there's enough pressure for it to break out again somewhere else. Right, so that is the data here for Kilauea, and that's kind of recapping what is going on with the volcano. We can take a little break here for some questions, and we are going to cover a little bit more of what might happen next and see some of the most recent photographs and that kind of thing here.
All right. Well, before we get into that, I do want to thank Hawaii Tracker helped make this possible. We do go through hawaiitracker.com. It's where we post all of our information, our updates, help to consolidate everything, put it in one place for you. If you like this type of content, you appreciate this video, make sure to like, subscribe, ring that notification bell, and make sure you get notified whenever we go live or post a new video. And if you consider making a monetary donation, we do take the super chats, but we also take them on hawaiitracker.com/support. I do want to shout out a few donations that came through there. Susan L, Katrin G, and Jana K. Appreciate all the support on both the super chats and the Hawaii Tracker support page. Really helps out. So we got a few questions here. Second, where are they? There we go. All right, so first, Sean has a question of what's the difference between the colors of lava, say between yellow and orange?
The colors, you mean the actual real color we're talking about?
Yeah,
or?
I believe the real color. He didn't say if it meant the thermal map or the.
Well, assuming
it's
the actual glow, like what color is a lava glowing? Maybe you can take it that way, right?
Yeah, that's what I'm thinking.
Often it's the chemistry of the lava determines like what color it glows, because it determines the temperature it needs to be to be molten. So different chemistry, different ingredients, different melting points, and different color of molten material. So that's kind of across different volcanoes. Sometimes on a single volcano, like back in Kapoho, you use the pyrometers to look at the color of the lava coming out, right? And that can be an indication of just plain temperature. So within one volcano, just plain temperature, how hot it's coming out. But if you're comparing one lava giant flow from one volcano to another one, for example, somewhere else in a different continent, then it might be composition.
All right. Richard asks, is there any evidence that no more magma is flowing into Kilauea? He thinks that it is still flowing.
Yeah, the evidence is that it is still flowing. Yeah, absolutely. Yeah. It's pretty common. The tilt meters, the GPS essentially have shown that after that first essentially 10 days of eruption, the volcano has been going back to work swelling, and essentially the whatever pocket that we popped for the eruption was separate, and the magma's been coming in ever since the whole time and not getting out to the point where the volcano is still swelling. That happens a lot with periods of elevated magma supply to the volcano, where when eruption ends and immediately you're inflating again, that's normal. And then there are other eras when you have low magma supply where you might actually have it quiet for a while. That's not what we're seeing. We're seeing signs that it's coming back in immediately the entire time.
We have two questions here about tilt meters, so I'm going to kind of combine the two of them. So, is there a long-term record of tilt plots from Maunaloa or Kilauea showing how it's changed, and that could help forecast the next eruption in any way?
Yes, so there is a long-term tilt record. For a long time in the early days of HVO, there was one set of instruments at the national park that essentially measured signals both from Maunaloa and Kīlauea. So you do have a little bit of a mixed, muddled signal, right? The modern era of tilt meters is much younger, where you have individual tilt meters at different places on the volcanoes. That's a much younger thing. So the record exists, but it's not very long. There are other ways to tell. You can, if you're looking at tilting of the ground, you can do that through a leveling survey, right? By just doing triangulation surveys over different times, and you can then plot azimuths of which way the ground is tilted. So all this has been compiled and synthesized in a USGS professional paper, 1806, by Thomas Wright and the other author, Fred Klein, might be the other one. Anyways, professional paper 1806 is the one that has all the graphs synthesized of all different methods. All the hard work's been done to try to put it all in the same plot, same kinds of plots over much of the volcano's history. So that said, Kilauea is the much longer record than Maunaloa. Maunaloa is always obscured a little bit more until the more recent era. Leveling surveys of Maunaloa began in the 1960s. That's really the specific.
Isn't there some like unspoken rule or spoken rule where it's not to use tilt meters for prolonged periods? They're best in 1 month intervals. If you want a longer duration, use GPS or some other instrument.
Yeah, we're talking about such a long period of time now that we're talking about getting tilt through various different techniques. Right. Each one has its own caveats. Absolutely, glossing all that over. So yeah, there are caveats for all these different techniques. Now, for example, when you're doing a leveling survey, you only can get within 5 microradians accuracy. A lot different than now when we're going down to the 0.1 microradian accuracy. So I mean, it's there's stuff plotted on there. It's the best of the knowledge. So you might miss the subtle details, but if a big eruption is coming, that's definitely picked up on the signals in one way or the other. Right. Old data is hard. Earthquakes are really tricky as well, right? We don't measure them in the same way, and we try to reconstruct. Well, this guy said his chair fell over, therefore it must have been this strong in this location. Therefore, it must have had this much energy release. It must have been a 5.7 or something. That's how complicated it can get.
Yeah, in the old tilts, I remember in 1955, that eruption in the Lower East Rift Zone. The tilt meter that they had to use during that eruption was in Pahoa, and it was one of the water tilts, which could only tell you, generally speaking, what's moving. It's not the highly precise and accurate tilt meters of today. So it's like two different instruments almost that like they just do not mesh at all.
Yeah, exactly. There's that wet tilt, there's the dry tilt, there's the modern. Yeah, there's all there's a leveling, there's all different kinds of ways to do it, and that's why they're not all the same thing, and certainly there are limits to every technique.
Sandra asks about the eruption in 2018, Fissure 17, the explosions that were happening. and we know about the different kinds that we heard at least. But is there any names that you've heard for those types of explosions? Proper names, and not the kind lava berg names.
For the explosions themselves or the noises?
Yeah, for the explosions themselves, well, the noise that's made by those explosions.
Yeah, the noises I really don't know as much. You know, for the explosions themselves, there's a whole classification scheme by how much material, how much power, how far, and all that, right? But that's pretty technical. You know, things like Strombolian or Linean or some, you know, like that kind of thing is. But that's not going to be useful to it. I don't think it's. I think she's describing more. You know. Yeah, that is a novel field. You know, the acoustics of volcanoes is something that's really more recently been valued, right? People have described stuff in the past in their accounts, but now we actually have acoustic monitors that monitor the volcano all the time. Right? The ultrasound, that's like a frequency of energy that the volcano can express itself on that can be detected. So without knowing the answer, you know, if I had to look into it, I would go look into into that field of the ultrasound monitoring and see if there's classifications in that whole field, but I don't know.
Till then, I'll place a placeholder and call it Big Bada Booms because I don't got anything for them. But yeah, I haven't heard any terminology for those explosions or the sounds from the explosions themselves.
Yeah. People obviously compare them to, you know, cannons or, you know, bombs or, you know, that kind of thing.
Yeah, the percussion from those is really the interesting part to me, that concussive force, that how far it would travel, like rattling windows so far away. That was the incredible thing.
I mean, you know, I've having been used to hearing the sounds when I came up here more than 20 miles away, I could still hear them on clear nights. That's how distinctive they were. And then, you know, anywhere within 5 miles, I could feel it in my gut, like my whole gut resonating in the inside. That low bass just permeating everything.
Right.
Really a huge amount of energy to feel sweep through you every time it happened. Every few minutes or however long it happened, you know, at some points in time.
Got a question from No One of Consequence, and I'm not making that up. That is their name. The question is how it's about the solidification process of the lake itself. We've talked about it before, but it'd be a good day to go over that again. How long does that process take to solidify such a large lava lake as we see now in the collapse pit of Holy Mau?
Yeah, that's in here. Let's that slide up. That's lined up for later, but we'll do it now. Right? So we have an analog from Kilauea here of a lake that in the end ended up being 440 feet deep. Ours is not quite twice that, but a lot more than that. And they drilled through the crust successively over half a dozen times and measured how far it was to the liquid lava under the crust. Here are the measurements: 20 feet in 1960, 43 in 62. And given that rate, it took 36 years for it to solidify. And the solidification temperature was 1900 Fahrenheit, 1065 Celsius. That's the answer there. 36 years for half the depth lake. We have a Volcano Watch article from 2019 about the Four Corners area and the Kapoho Lava Delta. And in that article, they do state that if you had a remaining thickness of that area of 232 meters, it would take over a century to fully solidify. So this is the kind of pattern. Pulls from the top first. Heat actually moving away, right, from the top easiest, but also to the sides and also down, because it's just pouring into a pit and there's cold rock that was all wet before it. So heat can go off in every direction, but easiest up. So it cools from the top down, the sides in, and stays liquid in the middle for decades. And in the case of our 750-foot deep lava lake, it may well be over a century that there's liquid lava in there. If, really big if, it can sit there undisturbed for a century, which is extremely unlikely.
Right.
We'll jump back into this later. Yeah.
Right. GW asks a follow up on that, and do you think that HVO is going to attempt to drill for core samples like they did at Kilauea in Halimamau now? And if so, how long would they wait?
I think it's a great question. You know, my gut immediate answer is no way. There's no way in a national park in 2021 you can get a permit to do that kind of thing anymore. But if that thing is going to be sitting around for possibly 100 years, it gives us time to think about it really hard and possibly change our mind and go through whatever bureaucracy is necessary. Because really, you know, these first data points aren't as interesting. You know, really, you can drill it once in the next 5 years. It's not going to take long. It's going to not be that thick. And if you can do it again 10 years after that, and then 20 years after that, that might be good enough. Because really, the value of this Kilauea data is immense. It's the only place in the world this has been done successfully. This was tried at Pu'u as well, but and in fact, it was tragic because a lot of the drilling was funded by the scientists themselves. And then the lava came and destroyed everything. And that was the end of that, fortunately. Burned up. So it's not an easy thing to do, because you might try to start the process of drilling it, and then something comes and it doesn't cool all the way to solid because it gets interrupted in between. And that's another reason why Kilauea is so unique. And yeah, we'll see. I just said how unlikely it is that that thing sits in Halimamau undisturbed for forever. So
right.
I
already placed my bet of it being 6 months before lava's back there, so I can't say that they're going to get a lot of time to go down there and start drilling.
Right. Yeah, it's, you know, this summit eruption ended up being longer than average, right? I mean, most summit eruptions are shorter than this, so
yeah.
There's a couple ways to take that. You know, maybe that's because of an increased magma supply, and maybe you can sustain more frequent eruptions that last longer. That's one way to take it. You could take it the other way and say, well, you know, if it just spent more energy now, it might take it longer to come back up, and it could be for a year, a couple years, a few years possibly. You know, of course that depends if the rift zone stays involved and if the south flank keeps moving and keeps making space. Because if the south flank keeps making space, there's way more area to put magma underground without having to have it erupt. And it also opens a possibility of upper east rift zone eruptions, you know, in that area that's in a national park as well. You know, you could have activity bouncing around for a little while as it adjusts all that before it can actually sustain something larger. So that's interesting to consider that.
Right. Well, I think that we can do the rest of the questions at the end of the program.
Sounds great here.
All right, back to you then.
All right, so let's switch to looking at some of the images released by the USGS, and go back here to May 26th as the release. May 25th images here. So here is the west vent crumbling on its southern side quite a bit here, and the remains of that western pond is right in here, and a couple glowing spots possibly visible from the S1 or the B1 cameras, seemingly under here and more likely under here at this point in time. I think this is the one that's most persistent now, and this one may have died off in the last couple nights here. Otherwise, everything is hard. There's still liquid under the surface there. It's just not going to be visible, and even won't be putting off any glow for a while. And then this over here is that eastern wall, northern wall, really northeast wall of that crater, which is where a lot of the gas comes out. It's been an area of gas venting persistently since the water lake was there, and now that the lava is covering that area, it seems to still be venting on the wall, but also through the lava a little bit in that area down in there. So that's zoomed in. Oh, I think scroll down. More zoomed out here. Seeing that northern wall around to the eastern side here, with all that gas release in there, and we'll be able to see this here shortly. This juxtaposition of the old steam vent with the lava level now. thanks to another image released by the USGS here in our sequence. And this is the next day of the release, and this is what I'm talking about. This is a series of before and after comparisons. So we have the Water Lake, December 20th. So the KW, Kilauea West camera. And then we have January 4th, the filling lava in the area there, before and after. Right? So I just wanted to point out here, this is here's that steam areas, that north wall before. It's still there. Skip it this way. Actually, you see a lot of it seems to have been cleaned off or scrubbed off. I wonder if during that initial steaming of the pond, if there was some interaction with that stuff that was in the wall and it got dissolved away or washed away or something, because it looks cleaner here in this particular image in January. And if I scroll down here, this is now May compared to December. You can see there the original north vent location right in there, clearly below the lava surface at this point in time. See a little bit of the west vent down here. That's the area that's just got drowned right in there. Back and forth. Kind of see here that lower part of that west, that northern gas vent is now underneath this crust, and why you might see the gas coming through that crust in this area especially, and then depositing minerals on that crust. And you might see discoloration of this whole area faster than everywhere else on the surface. This is great to play with yourself on a USGS site if you like. Then a wider view here of the lava lake on the 26th. And this is the view we'll get used to seeing for a while until something changes again. So no everyday changes anymore from the lava resurfacing, repaving it. And in the end, the big island in the center, a series of the early islets in the back, the levee still encrusted in there. You have a lot of lava flows along the perimeter of the ooze-out flows that come up along the edge. And you have a bunch of terracing, you know, a series of big cracks that separate that eastern half. And then lowest down in here, and terracing moving back in this direction, terracing back in this direction. And a weird combination of terracing and levees that are built as well, right? And it's interesting because the lava level is receding from the surface, but injecting underneath, so the crust rises up, and the terraces recede, but it eventually end up with a higher pond over the vent than so it's really funky topography in there. And there is a KW view, live camera view, in the last 24 hours with full moon streaking across here a few times. And in our last update, I did mention you can see a little bit of this wall seems to be glowing a little bit. I think it's just a bright moon reflecting on that white mineral over there. I don't think there's any glow or anything coming from there anymore. The one spot in the B1 camera was down here. It might still be glowing a little bit, but it's nothing major where you can see this whole wall. That's got to be the moon, that whitish surface there.
We have a $45 super chat from our friend Gary Bryan, who says, really appreciate the work you both put into these updates, as well as the 2018 review uploads. Thanks, guys. Thank you, Gary. Appreciate the continued support.
Well, Gary. Here's the S1 camera, and there's a spot you might see glowing, might be underneath there. Otherwise, not a whole lot changing there. In the B1 camera, West Vent is now at the far end of the lake, and the glowing spot is somewhere in here along that wall. Nothing really major either. Probably see, if we were to zoom way in underneath this ledge and this ledge possibly as well, some glow still persistent. Very small stuff here. This is essentially the end game. And of course, that's what we expect next is that cooling process to be the background process, and then what might happen next in between. So
We have a, sorry to interrupt there, but we have a $10 super chat from Les, who says, is there a possibility of a large weather event that can have an effect on the drying lava lake?
Probably not. Probably not. It's if you were to have a ridiculous rainstorm that was dropping, let's say, meters of rain, and maybe you might have enough water to do something interesting, like some small steam explosions, that kind of thing.
Right.
Or to pour water in there fast enough that you couldn't all steam away quickly enough. That can't happen here, that kind of rain, but not this time of year. It's not likely, and the more time goes by, the less likely that happens. Right? So think about Kilauea. Kilauea has been around for 62 years, and it hasn't had anything like that happen to it.
Right. And it's all about what your scale that you're looking at too on something like that. It's like adding a drop of water to a swimming pool, right? Did you really change anything, or was there any change at all? Well, yeah, there was some change, but is it worth talking about? Not really, right? Does it help the lava cool? Well, it doesn't make it hotter, that's for sure, but does it really do anything significant in terms of making it cool off quicker? Not really, not with that much insulation.
And really, the temperature of the water. The water can transmit. The heat capacity is different, right? But its temperature is not that different from the air or the lava. They're both very similar to lava. So
appreciate the question and the support.
Yeah, mahalo. So there's another volcano watch I wanted to bring up here, and this is back to January 2019 when we officially called the Pu'u era done after 2018 ended, and eventually everyone accepted that Pu'u was not coming back to life or not reactivating, and lava could come up near there again, but as before, I'll say, depending on where it comes up exactly, you could call it a whole new fissure, a whole new place, a whole new hill, and it may not be Pu'u per se, and that's a debate for the future. But in particular, I wanted to focus on its pauses, right? Because this article details the fact that there were, what does it say here? It's not on here, but I read here earlier, there were over 100 pauses during this eruption. So, 6 longest pauses during Pu'u activity were each 1 to 2 months long, and all between fountaining events. And ranged, for example, 65 days, 52 days, 50 days, 49 days, 43 days, 38 days, 10-day pause after Kupoinaha shut down in February 1992, and lots of other pauses, 11 days, 18, lots and lots. So this article was written after that 7-month gap, and by that point in time, they finally said, okay, it's been 7 months, we're not going to call it reactivating anymore, it's done, the end of an era. Right, so not a pause, that was too long, but that's just one example of what might happen, not unheard of, not just in Pu'u, but other eruptions as well. And this is in the Hawaii Volcanoes National Park website for Kilauea, and maps and things here, but I wanted to pull up this image they have adapted from HVO Professional Paper 1801, I believe it is. And what you see here is Kilauea activity. So duration of eruptions on the left, and then time across the top here. And where it's pink, it's essentially continuous the whole time, and only one era of an activity right through here. So it really is showing how often this volcano is active. At some points continuously, essentially. There's continuous. There's continuous as well. 2008 to 18, Summit Lava Lake, right in there. But really, in the last 100 years, we also have had longest gap from 1934 to 1952. That 18-year gap there is the longest gap we've actually had. And so how likely is it we could actually go 100 years without disturbing that lava lake? Seems very unlikely. In the last 100 calendar years, 40 of those years have had either a summit eruption or a summit collapse event, some subsidence event from some eruption somewhere else. So magma moves out from the volcano and then it collapses in. So in this more recent era where it's not been constant, it's still 40% of the years there's something going on that affects what's going on a summit. So that's the slow time. And then your high-end member is something's going to happen all the time continuously, and then you might end up having some kind of magma plug instead of a hard solid lava like it's right through there. And so of those subsidence events, go here to subsidence event. This is a 1960 collapse of Halemaumau. See, the upper caldera wall is up there. This is that inner pit of Halemaumau right there. There was a whole lava lake in here in 1952 that actually had another eruption on top of it in 54. And the middle of that lava lake was still liquid. And during a collapse event, through the lake, this is what the lake ended up looking like. That's the one from 1960. Here's a cross-section of what actually happened, right? So similar to Kilauea Iki, lava cooling on the top, on the sides, and on the bottom, on top of some older lava that was also all solidified because it came out in thinner layers and over more time. The 52 lava lake was deep and had that still liquid core. So when a collapse happens in 1960, it collapses down to the bottom, so lava drains from the bottom back into the volcano. But all these loose blocks in the middle get caught up in it and squeeze lava out of those cracks to flow on the surface towards the surface pit right in here. And so you really notice there's stuff draining down below that, down through here as well. So that looked like this. This is a view from 1960. And there is that liquid core of that lava lake getting squeezed out through cracks and pouring down into that new collapse pit surface there. So I mocked it up and put them both together. Scale. Get this to scale here. So you can see a little bit better how that would look. If that were to look today, you might see within that upper crater on that surface lava lake, cracking along the perimeters, and then cracking more in the middle, and then some pit, and then lava might drain into some pit. So just one possibility of what could happen, and I'm not in a hurry to share all different things, but we'll bring a little bit into the conversation every week here. So we discussed the cooling more so last week, and this week we can talk about more of this collapse process here. Keeping in mind that when lava cools, it contracts and can form void spaces, and we do expect settling of the crust somewhere on that lava lake at some point in time. Would not be surprising, right? And then, as well, we would not be surprised to see rock falls down the flanks of the crater walls onto that surface. Right? If you were to have a big enough block fall off the edge and bang into this thing, you might actually squeeze lava out some cracks somewhere as well. That's something that could happen as well. Not just a big rock falling down, but some big earthquake from below shakes this thing. Actually shaking it can cause bubbles to nucleate, like shaking a soda bottle. And then you can induce an eruption from an earthquake if you have all this magma sitting there, and especially if it's sat for a while and all the gas bubbles have had a chance to coalesce and emerge and actually get some potential. So that's something else to be aware of as well there. And that is going to conclude our discussion of Kilauea today. So Dane, any more thank yous and questions?
Yeah, we do have some more questions. I was going to type one up myself, but I'm just going to ask it before I forget it. So we were just talking about the 1840, the collapse that happened then, and then the subsequent collapses in 1843, right? And the something you were saying there, how the ground can move and lava can come up through a crack. Well, what I was thinking of is ground moving, but not lava going up through a crack, but lava coming down from the lava lake that's perched up there, draining back into the shallow system, right? And creating a localized collapse of the crusted top of the pie layer, basically.
Yeah, that's exactly what I
could
showed.
that? Okay, yeah. So, is there any differentiation between the two types of collapses like we had in 2018 and the one that you just showed in those old histories? Like, are we able to tell them apart? Like, this was this type of collapse, the summit flag sequence, other than just like, oh, well, there was an eruption in the rift zone that coincided with it.
Yeah, there's a lot of detail that's in there. It's not as well known in the 1800s for sure, but essentially the magma is leaving the area to cause a collapse, and so the magma can leave the area to either erupt somewhere else or fill some area underground, usually from the south flank moving. So if you see a big earthquake happen on the south flank, you could, depending on how much information you know, you could say, well, that's more or less this much volume got added to the magma chamber, and there is the difference in volume that you need to collapse, right? So if that magma from the summit area goes to fill that space somewhere else, then the ground on the summit collapses, right? And the summit's where you have the most magma accumulated, so that's the most likely place for it to collapse. So that's a possibility. That's why I wanted to bring up that 1960 image today, as a real thing that could actually happen. For, even if something doesn't happen at the summit, happens at Kilauea again, for example, or Kanakakoi, or an Upper East Rift Zone. Doesn't matter where it happens, you could still collapse the summit a little bit, right? Eruptions as far as 1960 was an eruption all the way to Kapoho is what did it. But it doesn't matter how far it goes. It's all about leaving the summit area. It could go to Maunaloa, for example, same kind of thing. Many of the events of subsidence
it has to go somewhere.
Are Upper East Rift. Yeah. So intrusion, eruption, intrusion could be associated with south flank movement as well.
All right. Eric has a question here. Actually, I'm going to go with this one first. Robert has a question. Do you think that the supply plumbing for the two vents that came up directly beneath the locations of the crater wall, or there may be some, have they maybe come up from farther away, moving horizontally between previous layers under the caldera floor to create those eruptive vents, or are they kind of just vertical cracks?
The way that the stresses work is it's trying to get vertical wherever possible. So if it has to go through a horizontal crack with a slight incline, it will do that. But given how cracked the rocks are on the summit, it probably doesn't have to go horizontally very far before it can find some path upwards again very shortly. Now the cracks that are there, it certainly can come incline. It could move, in a horizontal blade, but from a deeper part of it to a shallower part of it across the bottom of the crater. That's certainly possible as well. And you were curious to hear more. We'll probably wait more of the microgravity surveys. We'll wait the seismic studies. There's all kinds of data that was collected that at some point hopefully will give us some information about that.
We have a question here from Kelly that says, we're talking about Pu'u there for a little bit, and just talking about classifications, since we've talked about previously how Kilauea or Maunaloa can be determined active or dormant, or what is extinct volcanoes. But how does that work on something like Pu'u? Right, we've heard from USGS that they don't think Pu'u is going to erupt again, at least magma returning to that very specific event. Does that mean it's extinct, or do we have to wait the duration to get it to be there? Like, how does that work on a vent as opposed to volcano itself?
It's a vent, so it can't, it's just a part of the volcano, right? So we say that a volcano can be dormant or erupting or extinct, really, right? And then the vent of the volcano is the conduit for that to happen. But the vent itself isn't extinct or not extinct. It's a volcano that can be extinct. So you could say that the Pu'u eruption from the Pu'u vent is over, right? And maybe the vent, if lava were to come out of that same vent again, then you might say the vent's reactivated or something like that. But you really wouldn't at least in geological circles, we do say it all the time in barbecue, whatever, but you wouldn't typically say that Pu'u is dormant or extinct. You would just say that its eruption, that eruption from that event is over, and I guarantee lava is going to erupt near there again at some point in the future. If it comes out of that exact same hole in the ground or 20 feet to the side through the side of that cone, seems more likely to me. That's when you might, it's good. It might intersect the cone, and you might think, well, is it Pu'u or is it not Pu'u? It's likely the same rift zone system, but it's a slightly different place. And in the end, that's all technicalities of humans, how we name things, right? If it comes out 1/4 mile farther east, it's a different name thing. Geologically, it's exactly identical. Nothing was really buried there,
And it can get weird too, where it pops up like a half mile from Pu'u, and we're like, oh, okay, that's not Pu'u, that's X now, right? And then it erupts for 3 weeks, and then it migrates to near Pu'u, and then it's like, oh, okay, now what is it?
Yeah, there's a lot of gray zone. Yeah, exactly. To your point, Kupainaha was named and is actually by many considered to be its own separate eruption from 92 to 96 within the Pu'u era per se. But the Thanksgiving Eve breakout was halfway between Pu'u and Kupainaha, and it was termed event of Pu'u and not its own, right? It's not the Thanksgiving Eve breakout event. It's, the Thanksgiving Eve breakout of Pu'u event. And it did form its own little features there too, so it does get messy, right? But really, it's volcanoes that are extinct or not, and so saying that Pu'u was extinct perhaps might be misleading, because you might think, well, that means it's not going to erupt again right there, and that's absolutely not the case. Even if that exact hill doesn't erupt again, volcano will erupt there in that area again for sure. So that's why the whole volcano is what matters, and not just the fingertip of it.
So Eric has a question. I'm going to ask it, but before I do, just anybody watching know that we're not the cultural experts by any stretch of the imagination, and we're just, Philip has some knowledge, and maybe he knows something about this one. From a cultural standpoint, does Pele living on Kilauea and not Maunaloa in the mythology give some clues about at least the last couple hundred years of volcanic activity, volume and severity?
So I guess the first thing to say is that Pele is thought to, so the story is talking about Maunaloa first and foremost as the house of Pele. And Kilauea is more the latest thing, right? And if we look at the long-term eruptive trends, really Maunaloa was really doing a lot of work in the historical times and the Hawaiian times. And Kilauea has been more active recently, right? So whether that relationship says something about the relative activity in a volcano, is that it might, but the issue really is that Kilauea was right along the route from Hilo to Ka'u, and easy to get to, and just part of the roadside almost. Maunaloa is something, if something big is happening, you see it from everywhere, but if something small is happening, you just don't go by there unless you're trying. So it's a little bit different there. And that's certainly something that's held true in the modern era as well. We just don't have as much information on Maunaloa just because it's less accessible.
Definitely. Makes total sense, especially when you see how big Maunaloa is. That is a big volcano.
Yeah, so that's the best I can answer it. I can't go into the details beyond that. And like I said, there's others who could speak much more intelligently on this than me. But the first thing there is, that Maunaloa is the one that is associated with Pele first and foremost, more recently Kilauea. So really, it's both. And some people say like, oh yeah, like summer home, winter home, or they make that kind of modern joke on it, right? But really, Pele, wherever Pele goes, something volcanic is happening, is one way to think of it, as far as what the mythology and the cultural stories are capturing posterity.
We'll end with this question. It's kind of interesting. You have to do some envisioning. Says Chris from Facebook asks, Kilauea Iki's lava lake looks like a top of an angel food cake. Was this a result of cooling to gassing, or how do you do you expect the new crusted over lava lake to behave similarly? I believe that's where the sunken nature of it. Like I had to look up angel food cakes. I was like, oh, I haven't had one of those, and I don't know what he's. I'm like not sure what you're referring to, but I had to just check.
Yes, so there's a couple effects there, right? So one effect is that as lava cools, it can contract, and so you can actually pull away from the where lava is against the crater walls. It's normally attached to the walls, and so the middle part, where it's the thickest and contract the most, that's where it might sag and sink and pull apart from the edges like that. So that certainly can happen. It might take a while. It might be like a slow process where it's like a year, half an inch a year, something that will be visible at some point. It's not something we can see quite yet. That's one aspect of it. That should happen at Maunaloa as well. Kīlauea, however, did have a different process of the lava fountain erupting through the lava lake that was there, and so the lava level where it cooled was not the highest level that lava had been in a Kilauea eruption. Kilauea has a high lava mark as well along the edge, and so it kind of enhances the effect because not only do you have the contraction happening, but you have the high levy of the high mark of where lava was before. So really the edge is much higher than the middle. So hopefully answer that.
Makes
sense. There's
Yeah,
more happening at
makes sense.
Kilauea, but you will see something along those lines at Maunaloa over time as well.
All right. Well, I believe that does it for the questions and answer. I'm sorry if we didn't get to any. There's a bunch in the chat, but we're about at that point in the broadcast. We do have some announcements to make. We're going to be changing up the schedule starting next week a little bit based upon the yellow conditions on both volcanoes. We're going to be going back to once a week programming, and we're going to be doing that on Thursday. Yeah.
Yeah. So we'll switch to Thursday nights, and we'll do it like similar to what we did today. We'll balance it more if there's more on both volcanoes, but if there's one volcano doing something more than the other, then we'll focus on that one for the week. And at some point, they'll both, as needed, we'll adapt once again as well.
Right.
Yeah, we'll do on Thursdays. We'll change the announcements on the channel as well for that. But that is the plan. And same time.
I'm also go ahead.
Yeah, same time. So we'll aim for the same time. We'll keep the time the same at least.
Perfect. I'm also going to be changing the Drones On video series to release after that and going back to once a week as well. When I started out on the whole project, it was kind of like I was just going to take one video clip from one day and just talk through it. But then you can't tell the whole story that way, and there's just going to be huge gaps. So it's taking more time editing than I originally intended, but still want to do it right. And since we're not going to keep pace with the eruption anyways, might as well take the time and get that right. That said, there is one episode that's going to be premiering immediately after this live stream. It's the transition from phase 1 to phase 2 of the 2018 eruption. And it's just, it's like somebody flipped if you've been watching the series so far and you've been keeping track of everything and seeing how that changes from day to day, it's going to be like somebody flipped a light switch and the volcano really turns on when May 19th comes. So that'll be premiering immediately after that. Hope to see you guys there. That will be on YouTube. So yeah, check us out. And with that, I will pass it back to you. I believe that's everything I wanted to announce.
Yeah, mahalo Dane, mahalo for telling that story, and yeah, and definitely take your time, and we'll keep following along all summer on that Drones On series.
All right.
We will try to also keep putting out the short updates. I will likely put out a short video version of what we covered today here as well, or tonight as well. For those who can't make it, don't have the flexibility to make it through a whole live stream with us here. That's getting close to an hour and a half.
Right.
So mahalo everyone. Mahalo for all of you guys who supported us, who donated, chat, all the different ways. Mahalo, we really appreciate it. It really encourages us to kind of keep going. it's important to us to do that for our community anyways, but it's something that we've volunteered for. We're still largely volunteering for a lot of it. We still don't have our costs fully covered, but it's something we're happy to do for our communities, because at some point in time it's going to really matter more, and may affect lives, right? And something that in Hawaii we've been fortunate that we really haven't had people die a lava flows as is happening elsewhere in the world right now. Not to go into that whole tangent of it, right? But that just emphasizes how important this work actually is, to have communication channels open, so that people do need help. If they, trying it without help, they have some knowledge with what to do, how to move forward, and how to get assistance as well, rather than being completely helpless and it takes what it takes. That's what we don't want. We want to be able to be resilient. So that's not only the local residents here, but all the outsiders as well, who are it's as we saw in 2018, when eruption happens in a populated area, it's a global response, a global community that's involved. So definitely want to keep you guys involved as well, everyone, if you're not here. So appreciate all your support. That's why it means so much to us, right? Especially you guys are seeing what happened in 2018 and the impact to a resident in 2018 series there. So mahalo for that once again, Dane. And yeah, we will see you guys next week on Thursday. Tune into YouTube for the premiere. And until then, hui ho until we meet again. He's Dane DuPont. I'm Philip Ong. Aloha, everyone.